kind of object, really. And then we considered more advanced arithmetical expressions, like 10 to the 300, or maybe this expression here, or maybe something a bit more sophisticated with a triangle operation, or something even more sophisticated with one of these higher hyper operations, or maybe even something like this, where the hyper operation now is indexed with this 10 to the n plus 5, n to the 5th plus 3, something like this. It's a tremendously huge number, which we really have no control over, but nevertheless is something that we can write down. So this is a very wide range of possibilities, isn't it? I mean, we're starting with something really primitive and moving to something which is pretty sophisticated and really beyond our capabilities of understanding in any really kind of solid, meaningful way. And it's natural to think, well, is this just too wide a net? And I think we can acknowledge that casting such a wide net really does lead to problems. So one key problem is that most of our theorems about numbers and arithmetic start to break down and then fail as we move from small primitive numbers through to logarithmic numbers through to these mega huge mathematical arithmetical expressions for numbers. So in particular, here's a very important example, having to do with primes and the fundamental theorem of arithmetic. So we all know that every natural number can be factored as a product of prime numbers in essentially a unique way. That's the fundamental theorem of arithmetic. Now, even though it's been around for thousands of years, it goes back to Euclid, it actually is a little bit problematic. In fact, it's a lot problematic once we start getting to bigger numbers. This is a curious and disconcerting aspect of the way things are. So prime factorization is actually a technique that only really works for small numbers. And small numbers in quotes here, numbers, that are roughly familiar to us in our usual range of mathematical activities. A billion, a trillion, maybe a trillion, numbers like this. In this range, prime factorization is no problem. However, if we go significantly beyond that range, into the realms that we've been exploring in our last few videos, then sadly, prime factorization weakens and ultimately breaks down completely. It weakens and then ultimately it breaks down completely. For example, our favorite Z, 10 triangle 10 plus 23, almost surely has no well-defined prime factorization. The fundamental theorem of arithmetic does not actually work with this thing. So if we think of this as a number, then it's no longer true that every number has a prime factorization. This thing doesn't. And I'm going to talk more about this, but just to give you an initial idea. So here is a picture of the number line from 0 or 1 up to the Z, there it is up there. And say somewhere down here is 10 triangle 4. And this is not exactly a linear scale, but this is the range that we've seen that's sort of accessible to us in terms of being able to write things down explicitly in our universe. Even assuming we can deploy vast hard drives at Planck scales. Now, perhaps in God's garden, in some different world, where all of these numbers were visible, we can kind of imagine that for a second, or try to imagine that for a second. It's not entirely clear if that has any meaning, but let's just play this game. So imagine that we have God's garden, and in God's garden, we have all of these numbers, and there, perhaps this number Z does have a prime factorization. And the prime factors will, well, they'll be lots of them, typically, and so many of them will be in our range, these ones down here. We can find some of them. For example, 3 is a prime factor of this thing. Okay, so there will be hundreds, or perhaps thousands, or perhaps trillions of factors that we actually can't find. But there will also be lots of factors which are bigger, which are beyond 10 triangle 4, but still much smaller than this thing here. Okay, now when we look at this same factorization in our world, in our world, most of these numbers here are lost to us. We cannot write them down because they're too big to fit in our universe, no matter what arithmetical system we pick or choose. In particular, most of these primes that are appearing here in this ideal factorization are not really visible to us anymore. They're completely inaccessible. So even though this number, yes, we can write it down, it only takes a little bit of room. The primes involved in factoring it, most of them are going to be completely beyond us. This is very disconcerting, right? But it's a necessary consequence of the realization that